Hello everyone, thanks for joining today. So let's dive into the world of functional programming, which has seriously upped my scripting game in ServiceNow. I'm Amit Gujarati, your guide for today. Now I'm not a guru in functional programming. I didn't create a Lambda calculus and I'm fairly new to this myself. But that's exactly why I think this session will be valuable for all of us. We are on this learning journey together. Today, we will uncover what functional programming is, why it's a game changer, and how it helps us to craft neater, more efficient code, particularly in ServiceNow. So let's get started and have some fun with it. I've heard about functional programming from my mentor Gurpreet. Okay, so I started asking myself, what is functional programming? And the first thing I learned is that it's a bunch of buzzwords. Words were flying all over the place, like higher order functions and statelessness and referential transparency, immutability, side effects, and there is a lambda character that keeps showing up everywhere. So it kept me guessing what it has to do with coding and how it can make my life easier at work. So what's exactly functional programming? Broadly speaking, it's a coding style that a certain language supports. Luckily for us, JavaScript is one of those languages, which means we can apply this principle to ServiceNow scripting as well. So, what sets functional programming apart? We must have discussed in the past, okay, in our curriculum about imperative and object oriented programming before, but functional programming introduces a different approach. It's a programming paradigm. This leads me to wonder what exactly is a paradigm. It turns out a paradigm is essentially a worldview. It's how you perceive and interpret what's around you. And for us as a programmer, it shapes how we see our code. Understanding the component of our programs and how these elements behave and interact. In essence, adapting functional programming is like adapting a new mindset. It's a fresh way of looking at the programming challenges we face and tackling them with a different toolkit. Let's quickly break down some familiar programming paradigms. First, imperative programming, which focuses on commands guiding program through a sequence of tasks where timing and order are the key. Then we have object-oriented programming, which builds on by grouping complex state into an object that interacts through method, helping managing more integrate system. Then we have functional programming, on the other hand, is a subset of declarative programming. It shifts away from the command to outcome, emphasizing what the result should be rather than how it should be achieved. Like in SQL, it prioritizes functions without side effects, setting it apart from state-centric approach of other paradigms. Yet defining functional programming is its entirely still poses a question, right? So what really is the essence of functional programming? After peeling back layers of buzzwords and academic jargons, it turned out to be quite straightforward. At its core, functional programming revolves around a singular yet profound concept: the use of pure function. This simple idea is both powerful and foundational, guiding how we can approach and structure our code in a functional programming. Cool. So what's pure function then? So pure function is a function that only depends on its input. It doesn't look at anything else from the outside world except the argument you pass to it, and it returns its output. That's the only thing it does. It doesn't have any other effect on the world. It doesn't make any changes than returning its return value. Let's break down an example of an impure function called greetUser. Why isn't it pure? Okay. First, it doesn't take any argument, which can be a hint that it might not be a pure function. Looking deeper into the code, we see it uses a variable username, which holds the string John Doe, defined outside the function. Since greetUser depends on the external variable, it's considered impure. It's relying on something outside its immediate scope. Another big giveaway, if you see, of its impurity is that it doesn't return any value. Instead, it logs a message to the console. This action is known as side effect, affects the world outside its function scope. by changing what appears on the screen. Moreover, if we alter the username to Jane Smith and call greet user again, it outputs a different message despite being called in the exact same way. This variability confirms its impurity, as a pure function would always produce the same output for the same input. Okay, let's now look at a pure version of the greet user function. In this case, the function takes in name as an input argument, which it needs to perform its task. Instead of printing it to the console, it returns the greeting as a string. This function strictly uses its input to produce an output, which it then returns. If you call greet with the user John Doe and then again call it with the same name, you will get the same result each time. This consistency confirms that it's a pure function. Later in this talk, we will explore more about how to use this principle to write functional program, introducing some additional patterns and technique that can help us guide and build cleaner, more predictable code. But first, let's take a step back and look at why we might want to be doing this. Why is functional programming cool? So, maybe some of you have already been convinced that functional programming is nice, but maybe some of you are like, I don't know. This seems like I have to gotta think about, okay, I just can't log to the console. That's super convenient, so and so forth, right? So why would I not want to do that? One thing is that pure functions are really predictable because, as we saw, the only thing they depend on is their input, and the only thing they do is return their output. So, if you know what the function look likes and what's going into it, you can really easily predict what's coming out of it. With pure function, we will always have more predictability than the impure ones. Like with my first impure version of great user. If I change name, what do I get? I don't know. It depends a lot on the other things. Right? This means functional programming makes code safer. It's harder to introduce bugs in your code. But it also means that it's easier to test your code and find bugs if and where it occurs. That's because when you are trying to test a pure function, all you need to do is pass in your test input and check if the output is what you expected. You don't need to set up a whole imaginary world, okay, with all the states and mock objects and ever then try to recreate the state of the world when you call this function. No, you just need to pass in whatever values you might expect and check that they give the right thing. And if they don't, then it's easy to track down, right, where the bug is. Because you know that if the inputs are right and the output is not what you expect, okay, the problem must be within that function. It's not caused by some interaction with the some other part of the program somewhere else. So this makes it easier to track down the problem. So these are the good reasons to do functional programming. Functional programming is great. Use it for predictability, the testability, the ease of debugging, but don't use it because it makes you feel cool or smarter programmer in the house. Okay, so let's press on so that we can get closer to it. Let's do some functional programming. How do we do that? We write a pure function. Okay, how do I build a program out of pure functions? Well, we are gonna look now at few principles you can live by as you are starting to write your first function program. Kind of guiding lights, as it were. And the first one, maybe it's obvious, but I think it definitely bears mentioning. You should do everything with functions. Your program is going to be a function which may be made up of another function, which may be made up of other function and still other function. So it's function all the way down. The idea behind functional programming is that everything, the whole world, is function that talk to each other. As we were saying, paradigm are about what the world is made up of. Functions. How do those components interact? By taking input and returning output. Here's an example of imperative program that does not use function to create its world. We have city, got greeting, and are basically telling the computer, remember there is a string city, remember the other string greeting, and log this. Concatenate this string together. So I log something to the console. I get something out. Then maybe I want to change the greeting. Let's say forget hi, remember hello, and log the concatenation again. So we get hello Pune. Anyway, it's not a functional. Okay, we are not defining any functions here. We are using the gs.log function, but as we said, that's already a kind of not very pure function. So how could we do this in more functional way? Well, we could turn our program instead of series of command into a function that I can call again and again. This time we are gonna take in a greeting and a name and then return a kind of concatenation of all those with some punctuation in there. So now I can run my program by calling my function greet, passing in the input hi and Pune, and I get the output, the string as hi Pune. And I call the same function with different inputs and get a different string. Put in hello. Okay. So this is what you end up doing. Thinking about everything in terms of function. It's sort of like that saying, you know, when all you have got is a hammer, everything looks like a nail. Well, in functional programming, everything looks like and is a function. You just see functions everywhere. And we said that this should be a pure function. So one way we can ensure that we are writing pure function is by trying to avoid side effects. So what side effect? Well, we mentioned earlier that a side effect is something like gs.log, which does something other than returning an output value. So what we want to do is avoid that. We want to do nothing else in a function beside compute and return our output. Here's a function with some side effects. I've got this object conf, it's got a name, it's got a date, and then I have a function called rename conf. It takes in a new name, and the first thing it does is assign this new name to be a value of conf.name. Warning, side effect. This is our first example of a side effect because it's changing something in the world. It's changing that conf object that I have declared earlier. That's outside of the function, but it's not a return value. Then it's got another side. I'd like uh, write logging something to the console. We had talked about that example earlier, and again, we see a huge red flag. It's not even returning anything. The only thing this function does is causing side effect. When I call this function rename con, I get my first side effect. I get the console.log message that I renamed it. Cool. And then if I check what the conf is, I see that it's changed from what I originally assigned it to be. This is bad because maybe someone else was depending on this conf being the way it was originally. Maybe they were not expecting this change. Here's how you can achieve this without side effects. Now I've got a new function or rename con, okay, which this time takes in an old con and as one of the input along with the new name. What it does is instead of changing the value of the original con, it returns a new object that also has a name and date. So it looks the same in structure as the original con, but it got new name and the old date. The only useful thing this function is doing is returning a value, which I can then capture as a new con and I can verify. Yep, okay, new conf is what I expected. It's got a new name, but my original conf is still the same. This is an example of function without side effect. This will help you a lot in writing a neat code. Another thing that we saw in the last example was that in the side effecting function, We were changing something in place. That's called mutating data. Changing it in place. So we want to avoid that. We want to avoid mutability and mutation in functional code. The little Rami mantra that I like to think of for this is that you shouldn't change something in place. Instead, you should replace it. We found that in the last example, where instead of changing con, we created a new con that we could use to replace the old version. Let's consider we have an array of ServiceNow modules and we receive a request from our manager to change the change module to manage hyphen change. I need to update something in my module array by replacing the value at index 1, appending manage hyphen to it, and reassigning it as the value at index 1. Now the module array appears different but is fundamentally the same. This change is risky because a coworker might have been using this array with specific expectation regarding the format or content. Probably the validation for them will break with the hyphen, right? If they find the array altered unexpectedly, it could lead to bugs, complaints, and no fun for anyone. So it's best to avoid this approach. Instead of altering existing module array directly, we can create a fresh version of it. Here's what I am doing. I'm using the array.map function to generate a new array that includes the updated value we need. The map function is quite interesting and versatile. We'll dive into it bit more later. It works by applying a function to each item in an array. Each time this function is applied, it returns a new element that goes into the new version of the array. So all I need to do is provide a function that checks if the value is changed. If it is, it doesn't just return the original value. Instead, it returns a new value, which is concatenation of manage hyphen to a change, resulting in manage change. All other value remain unchanged, okay? And this process results in a new array called new module. In this new module array, we have incident, manage change, and problem. But if you check the original array, it's still intact, exactly as it was before. So no one is upset with me because I haven't disrupted anyone's work. This technique of creating new version rather than modifying existing data in place is a hallmark of functional programming. You'll find it a valuable habit as it prevents side effects that can lead to bugs and frustrations. However, there's a bit of problem with that, especially when we consider performance and efficiency, which we touched on earlier. So let's think about this. When we have an mutable data, let's take a regular old JavaScript array and call it as foo because it's simple name and everyone likes simple name, right? So it contains some family numbers like 0, 1, 2, 3, 4, okay, till 7. But maybe I'm not very of the number 0 because it can act strangely, right? When you try to divide or multiply it. So I decide I don't want any zeros around anymore. I'd like to change it to an 8. After all, they are both round numbers, right? This is perfectly fine in a world where data can be mutable, okay? Because I can keep the same array while all the other numbers remain unchanged. I can switch it back or change it to an 8 as I needed. It's still a 0. Now it's an 8. Even though it might still look like the same old 4, nothing else seems to have been changed, right? Cool. But here is a catch. What if someone was expecting that 0 to stay as 0 and now it's suddenly an 8? It's completely different scenario now for them. And understandably, they might be really upset with you. So I can make this array immutable, meaning it cannot be changed once created. This is how this isn't how JavaScript array normally works. But imagine an array that fixed in place to change a 0 to 8. I've created a new array for 2. Okay, let's call it as 2. Where the 8 is replaces the 0. but everything else stays the same. These methods keep users of the old foo happy because they see no changes. However, it's insufficient because it requires extra space for new array and time to copy all the unchanged elements. This this might not be a big deal for a small array, but when we are working on practical scenarios, right, with millions of array or larger ones, the inefficiency could become significant. So I can offer an immutable array, which means once it's created, it can never change. Now there is an interesting concept called persistent data structure, also known as immutable or purely functional data structure. For discussion, let's refer them as persistent immutable data structure. This approach offers an efficient way to manage immutable data. So the insight here is that instead of using a regular old array, what if I represent my array? Okay, imagine our data as a special tree called a foo, where each leaf holds value. These leaves are connected by nodes, okay, that link up to the top node, uniting all leaves into one tree, which mirrors our original array. Now, when we need to update a value, we don't redo the entire structure. Instead, we just copy the specific leaf node, okay, affected. It's quick, it's efficient fix that keeps the rest of the tree intact. So, when I modify a node in an immutable data structure, I only need to copy the node that directly connected to the change node, all the way up to the tree root. This requires some extra work and space, but not as much as you might expect. Okay. The reason is that I don't have to duplicate the part of the tree that haven't changed. This is known as structural sharing, where most of the tree is shared between the original and the updated version. We maximize the reuse of the existing data structure. This is really exciting because it shows how functional programming doesn't just deal with abstract concept. It's about emphasizing optimizing our program by using data structure that are designed to be immutable and efficient. We significantly boost performance, addressing one of the key benefit we have discussed earlier. So the next functional principle I want to talk about is avoiding iteration, which for me was one of the toughest concept to grasp when I dived into functional programming. In functional programming, you generally avoid using iteration. Instead, you use recursion to achieve the similar outcome. Here's a familiar scenario. I have some function that sums an array of numbers using a for loop. It starts with a variable I set to 0, increment it with each iteration, and sum the number accordingly. With each loop, I changes its value. This practice of modifying the value and variables, okay, like changing I in the loop, isn't typically the functional programming. Instead, functional programming often uses a recursive function approach to achieve same same result without altering variable states. So here is an example of recursive function. While it's not the only method in this approach, we start with an array of number. Like most recursive functions, there is a base case. In this case, if the array has only one item, we simply return that item. If the array has more than one item, the recursive case kicks in. We take the first item and add it to the sum of the remaining items. This means this sum function call itself within its own definition. By doing this, it processes each item in the array until one item is left. Then return up through each call with the total sum. This recursive approach achieves the same result as the iterative method we typically use. Think about recursion is the key in functional programming. It might be challenging to grasp at first if you are new to recursive functioning, but starting with simple example like this can really help. Another consequence of not using iterative loop, okay, because people will be really upset with me, is that you will need some other tools to effectively process everything in an array. Three of the tools you will find incredibly useful are functions like map, reduce, and filter. These are fundamental tools in a function programmer's toolbar. Many folks, including myself, initially find this a bit challenging to grasp. The best metaphor I've encountered, okay, and it helped me a lot to understand this is map, filter, map, reduce, sandwich, which we'll be seeing in the next slide. So there is a useful concept called the filter, map, reduce, sandwich, which you can see on the screen. That really helps illustrate how this function works together. Let's imagine we have an average array of ingredients. Because I'm in a mood of making delicious sandwich. So first, to make sure I get only ingredients I like, I use a filter function. So this function checks each item against a condition, returning true if I like the item and false if I don't. So ingredients like cucumber and onion, which I don't like, are filtered out. The rest move to the next step. So what filter function does, it just filter out the data. Simple, right? The next comes the map function. Here I take the approved ingredients and prepare them for the sandwich. For example, whole vegetable might need chopping or slicing. So I use map function to transform each one into a more sandwich friendly form. So what map does, it converts your array into a different form. Simple as that. Finally, I use reduce function to assemble the sandwich. This function takes all my prepared ingredients and combine them into a final product. For instance, it might stack all the chopped ingredients to create a neat layered sandwich. And that's how you use filter, map, reduce to make a perfect sandwich. Filter, map, and reuse are not just useful, they are essential. So it's crucial to understand them well. These functions are called as higher order functions because they either take other function as an input or return them as output. What exactly is higher order function then? Simply put, it's a function designed to work with other functions, either by accepting them as argument or by producing them as a result. To effectively create and utilize higher order functions, we need a programming language that treats function like other data types, such as string or array. This capability is known as having a first class function that can be passed around as values. Luckily, JavaScript support this, which many of us already familiar with. We often use callback, right? For instance, by passing them into other function. This is a typical example of higher order functions in action. In functional programming, other interesting pattern you will come across is closure. Let me introduce you to a neat higher order function called make adjectivier. What it does is pretty good. It takes an adjective and returns a new function. This new function then takes a noun and returns a string that combines the adjective and the noun. For example, if I create a function called holify, okay, by using make adjectivier with the adjective holy and then use holify on a noun like JavaScript, it, re- it results in holy JavaScript. And if I use it on cow, it returns holy cow. Yes, functional programming can indeed include a dose of dad jokes. What really intriguing about the holify function is that it remembers the adjective holy even though it's no longer directly provided as an input. This memory is called as a closure. Closures are a powerful concept because they allow a function to remember and retain access to the environment at the time it was created. This isn't just a theoretical concept, it's a practical tool that helps maintain state in a pure way without direct side effect. Make Actify is a perfect example of higher order function that utilizes closure to encapsulate and carry context forward. Okay, the last point I want to make uh, about how we can write functional programming is that one thing that really helped me when I was starting writing functional style is to imagine program as a data flowing through a series of functions. Picture it as a pipeline. or an assembly line where the data comes in, get transformed by one function, then pass on to the next function and so on. This way, our program systematically processes data, transforming it step by step until we achieve the desired result. At each stage in the pipeline, the output of the first function becomes the input for the next. This process continues with each function, building upon the last until the final output is produced. Here's an example of using higher order function effectively. Consider a function named ender that takes an ending and returns a function which appends this ending to a string. For instance, adore adds rock, announcer appends yal, and exclaimer ends with an exclamation point. We can combine this into a function called hype. This function takes any string, applies adore, then announcer, and finally exclaimer. For example, calling hype up on jazz, resulting in jazz rock sol. This method, where we change this enhancement, is known as function composition. It's like building with Lego blocks, stacking small functions to create something more significant. Thank you. So this is all for functional programming today. Okay.